You went over some probability concepts yesterday, and sure enough, this homework problem is a classic probability question. So let's take a look and see how you did on this one. So here's what it says. Joe and Matthew plan to visit a bookstore. Based on their previous visits to this bookstore, the probability distributions of the number of books they will buy are given below. So it looks to me like this first distribution is the distribution of number of books for Joe, and the second distribution is the number of books for Matthew. And it looks like they're either going to buy 0 or 1 or 2 books total. So here's what the question says. Assuming that Joe and Matthew make their decisions independently, what is the probability that they will purchase no books on this visit to the bookstore? Okay, let's think about it. If they purchase no books on this visit to the bookstore, that means that Joe is buying no books and Matthew is buying no books. So if I were to use some probability notation here, I would say it's the probability that Joe is going to be purchasing no books and that Matthew is purchasing no books. Now, we are told here that those decisions are made independently, which means that for an AND problem like this, we are allowed to just simply multiply probabilities. So if we look at Joe's distribution, there's about a 50% chance that he would buy no books, and for Matthew, 25%. And we want both of those things to happen, the first one and the second one, and because they're independent, we can just simply multiply those two together. 0.50 times 0.25, and that'll give us an answer of 0.125, which if we look at our answer choices, sure enough, answer choice B is the correct answer there. So hopefully you did okay on that homework problem from yesterday. And I think we are ready to jump into our new learning for today. And as usual, I'm going to start out with some very clear expectations for what we're going to accomplish today. And today we have only 2 learning targets. All right, so here's what they say. The first one says, describe a binomial distribution and be able to perform probability calculations for binomial distributions. And then the second learning target is just a parallel learning target. It looks almost the same as the first one, but now we're talking about geometric distributions. And once again, we need to be able to do probability calculations. So we're still under the general umbrella of probability, much of the stuff that you talked about yesterday with Mr. Murphy, but very specifically today, we're going to be talking about the binomial distribution and the geometric distribution. And I will make sure that at the end of the lesson today, we come back to these 2 learning targets to make sure that we have what we need. So let's jump right in. So here is the question to be answered for today, which I think is one that you can relate to. The question is, how many AP Stats students are YouTubing? And what I'm wondering is how many of you AP Stats students out there in the country are actually using these videos as part of your AP exam review in order to prepare for the AP exam on May 22nd. So here's what it says. It says, according to YouTube Analytics, 30% of all AP Statistics students are using YouTube as part of their AP exam review. Okay, now this number right here, 30%, is a proportion rather than a mean, and it is a proportion that is claimed to be made for the population of all AP Stats students. So if we're being careful about our notation here, we know that it's a proportion, and we know that it's a population proportion, so we should be using P here rather than P hat. And we're going to say that our P is 0.30. Now let's continue reading here. To investigate this claim, the College Board is going to take a random sample of 80 AP Statistics students. Okay, let me pause right there. 80 is our sample size. So typically we will use lowercase n for our sample size. We're going to have, a sample of 80 AP Statistics students. And then use a survey to count the number, this is important, the number that are using YouTube as part of their review. So let X equal the number of students in the survey that are using YouTube as part of their review. So the College Board is going to reach out to 80 students, get their survey results, and count up the number out of those 80 students, how many of them are using these YouTube videos as part of their exam review. So question number 1 says that show that X is a binomial random variable. Binomial random variable. Well, if you want to show that something is a binomial random variable, there are four conditions that must be met. So let's list out these four conditions, and then we'll go through and check each one of them individually. So the first condition is what we're going to call the binary condition. And binary means that each trial can either be categorized as a success or a failure. And when I say trial here, I mean each individual AP Stat student that's part of the sample. And sure enough, we could categorize them as a success if they're watching YouTube, a failure if they're not. So we're going to say here that each trial is a success, and we're going to make it clear that a success here means that the student is using YouTube, or a failure, no YouTube. So we would say that that condition is satisfied. The second condition is what's known as the independent condition. Now, what we want to know here is that the result from one student is independent from the result of the next student. So we're going to say here, each trial is independent. Now, there's a couple of things that we need to consider in terms of independence. The first of which is that we do have a random sample here, which is going to ensure that the results of one student are not going to impact what the next student might say, because it's just a random sample of 80 stat students from around the country. So that's good. The random sample ensures our independence. But there is one other thing that we need to consider when it comes to independence, and it's the fact that here we are sampling without replacement. In other words, once a student has been selected as part of the sample, they are not put back into the pool to be selected again. They can only be selected once. And so we know that when we take a person out, that is going to change the probability that the next person would be a YouTuber by just a tiny, tiny amount, right? And the amount is small because this sample size that we have, 80, is very, very small relative to the whole population of over 200,000 AP Stat students. So we actually need to check something here that is called the 10% condition. And this is true anytime you're sampling without replacement, we want to check the 10% condition, which just says that the sample size is less than 10%, which I'm going to write as 1/10, the population size. And in this particular case, 80 is our sample size. And the population here is all AP Stat students, and there are well over 200,000 AP Stat students. So I would definitely say that the sample is less than 10% of the population. And therefore, we're going to say that the independent condition is satisfied. Next up, condition number 3, we're going to call it number, but then I'm going to finish the statement in here and say that the number of trials is fixed. So the number of trials here is the sample size, right? We have 80 students, which represent the 80 trials. And so we do know that that number is fixed because we are taking a sample of size 80. So we would definitely say that that condition is satisfied. And then finally, condition number 4, which is known as the same probability condition, says that the same probability of success on each trial. And actually, we know, according to YouTube analytics, 30% of AP Stat students are using YouTube. So that probability of success, P, is 30% for each student. And so we would definitely say that the fourth condition is satisfied there. And sure enough, we have a binomial random variable. So let's move to question number 2, which says, what is the shape of the distribution of X? Well, very often with a binomial distribution, you're going to have one value that has the highest probability, and then as you move farther away from it, the probabilities get less and less. And sometimes the shape of that distribution is going to be approximately normal. And the way that we can check that is using what's called the large counts condition. So let's go ahead and check the large counts condition here to see if that is satisfied. And the large counts condition says that n times p is greater than or equal to 10, and that n times 1 minus p is greater than or equal to 10. Well, let's plug in some numbers here. n times p is just going to be 80 times 0.30, and that's going to give me 24. And sure enough, 24 is greater than or equal to 10, so we're good there. Now let's check n times 1 minus p, which is going to be 80 times, and 1 minus 0.30 is going to be 0.70. And for this one, we're going to get 56. And sure enough, that's greater than or equal to 10. And if we just think for a second here what these numbers represent, 24 is really the number of successes that we expect to get, right? 80 trials, 30% of them should be successes. That would be 24 successes. And this number over here, 56, represents the expected number of failures. So if the expected number of successes and the expected number of failures is greater than or equal to 10, then the large counts condition is satisfied. And what we can say then is that the distribution of x is approximately normal. So we have now the shape of our distribution. Okay, next we're going to move into the mean and the standard deviation of a binomial random variable. And I'm going to give you a little bit of a hint here. On the formula sheet, which you will be allowed access to on the AP exam, there is a section of the formula sheet that you can see right here, shows you everything that you need to know for a binomial distribution, including the formula for the mean of a binomial distribution and the formula for the standard deviation of a binomial distribution. So let's go ahead and record that in our activity here. The mean from our formula sheet of a binomial is n times p, and the standard deviation is the square root of n times p times 1 minus p. And so now it's just a matter of plugging in some values and seeing what we get. So let's start with the mean, which is n times p. And we know n is 80 and p is 0.30. In fact, we already talked about this value, right? 24 is the expected number of successes. So if the College Board were to take random samples of 80 over and over and over and over again, then on average, they would find 24 students that are YouTubers. Now to the standard deviation. According to our formula here, we need the square root of, and then we need n, which is 80, times p, which is 0.30, times 1 minus p, which is 0.70, and then we take the square root of that whole thing. And I've already put that in my calculator. I got an answer of 4.1. So what that standard deviation is telling us is that if the College Board was to repeatedly take samples of size 80, then the number of students that are YouTubers is typically going to be about 4.1 away from the mean of 24. So it seems reasonable that we would get values a little bit bigger than 24, a little bit less than 24, right? If they typically vary from that value by 4.1. All right, now let's move on to number 4, where we're going to do our first probability calculation here. It says find the probability that the sample has exactly 32 students who use YouTube. Well, once again, I'm going to take you back to this formula sheet here because it has something that's very useful to us, and that's the probability of getting a certain number of successes. So we need this big crazy formula that you see right here. So let's go ahead and copy that formula to start back in our activity page here. Just going to put this out in the margin. The probability that we get X successes, right, out of our n trials equals. Now, the first thing that you see there on the formula sheet is this n over x with the parentheses around it. Now, some of you may know that as n choose x, right? That's a combination. We're actually going to use the calculator to help us find that. And then let's finish the rest of the formula here. It's the probability of success raised to the number of successes times the probability of failure raised to the number of failures. So even though it looks kind of crazy, that formula, once you plug the numbers in, it seems to make quite a lot of sense. So let's see what it looks like for this particular problem, where we're trying to find the probability of 32 successes. So here's what it would say. The probability that x is equal to 32 successes. Well, according to the formula, we need to do this combination first, which is really just going to tell us how many different ways are there of getting 32 successes out of 80 trials. times the probability of success raised to the number of successes, which is 32, times the probability of failure raised to the number of failures. Well, 32 successes means we're going to have 48 failures in order to add up to 80 there. Now, this is something you would definitely need your calculator to help you with. So let's just go ahead and jump over to the calculator now. If you have yours available, you can grab your calculator. If you don't, just follow along with what I'm going to show you here. But we're just going to take that whole formula there and plug it into the calculator. So the first thing we need is the combination. So you're going to find that over here if you hit math, and then you go over to probability, and it should be the third one down there where you see n choose r. And for us, n, there are 80 trials total, and we want 32 successes. So you're going to do 80 choose 32. And then we want to multiply that by the probability of success, which is 0.3, raised to the number of successes, which is 32, times the probability of failure, which is 0.7, raised to the number of failures, which we know is 48. And we have our final answer here, which looks like it's about, let's say, 0.015 would be the value that we're getting here. Now, I am going to show you a little bit of a calculator shortcut here, another function that you can use in order to find this same value. So here's where you're going to find it. If you go to second vars, which is your distributions menu, and you scroll down a little bit, you're going to find a couple of commands here that include binomial. And I'm going to tell you we want the first one, which is a binomial PDF for probability distribution function. And I'll explain why in just a minute. But we're going to use binomial PDF. Now the calculator is going to ask us for a couple of things. We know that the number of trials is 80. We know that the probability of success is 0.3. And the x value, which is the number of successes that we're looking for, is 32. Go ahead and paste that onto the main screen. And sure enough, we get exactly the same answer as if we had used that big, long, crazy formula. So we know for sure that 0.015 is the correct answer on that. So let's jump back to the activity and fill in our answer for that. And then I'm going to give you a little bit of an AP exam tip if you want to use that calculator function as part of your work. So in the activity, let's record our final answer here, which we got 0.015 was the answer from the calculator. And then I'm also going to record the other way that we did it on the calculator, which was using this function called binomial PDF. Now, if you're going to use this on the AP exam, you have to be very clear on what each one of the values represents that you typed into the calculator. So that first thing the calculator asked for was the number of trials. So I'm going to clearly indicate here that we typed in the number of trials n is 80. And then it asked for the probability of success, which I'm going to write in as p equals 0.30. And then it asks for the number of successes, which for this particular problem is 32. And sure enough, the calculator reported the same value as if we had used the formula. So your AP exam tip here is if you're going to use this calculator command as part of your work, make sure that you're identifying each one of those parameters inside the parentheses. Okay, we are ready for number 5, which says find the probability that the sample has at least 32 students. Okay, which is not the same as the previous question, which asked for the probability of exactly 32 students. Now I want at least 32 students. So if I were to write a probability statement here, what I'm looking for is the probability that x is greater than or equal to 32, right? At least 32. And if you think about that, at least 32, well, that means that it could be 32 or 33 or 34 or 35. So I'm going to write that out here by saying that this is just the probability that x equals 32 plus the probability that x equals 33 plus 34, 35, 36, 37, all the way up to the highest possible value that x could be was that all 80 students were YouTubers. So the final term here would be the probability that x is equal to 80. Now we could go through and calculate each one of these probabilities. In fact, we've already done this one above, right? We know the probability of exactly 32, But then we would also need 33 and 34 and 35. And you can quickly realize that we are not going to do this by hand. We need some technology help here from the calculator. And in order to use the calculator, we have to turn this into a statement that uses less than or equal to, because that is the command on the calculator. Binomial CDF gives you less than or equal to. Well, it's pretty easy to flip this one around, right? If I want 32 or higher, the values I don't want are 31 or below. So I can use the complement rule here and say 1 minus the probability that x is less than or equal to 31. And that should give me the right answer. Now that x is less than or equal to 31 is where we're going to use the calculator function. So let me just set this up for you, and then we'll jump to the calculator to see what the answer is. We're going to do 1 minus, but this time we're going to use binomial CDF for cumulative distribution because it's the cumulative probability all the way up to and including 31. And remember, we would have to indicate our values here. So n equals 80, p equals 0.30, and x equals 31. And well, let's go to the calculator and see what the calculator would give us for this one using the binomial CDF. So I'm going to do 1 minus, and then remember it's second vars, that's your distributions. And also remember that this time we want binomial CDF rather than PDF. Still got 80 trials. Probability of success is still 0.3. And the x value this time, we want 31 and below. And we're going to subtract that from 1. And we are going to get an answer here of 0.036. 0.036 is our answer here. So let's jump back into the activity and fill in our answer there. And then we've got one last question to fill out for this binomial distribution. So our final answer here is 0.036. All right, on to the last question here. Number 6 says, College Board selected a random sample of 80 AP Stat students and found that 32 of them were using YouTube. Okay, let's just pause for a second here and think about this. They took their sample of 80, they got 32. Well, how much were we expecting them to get? If I look back up here at my expected value or my mean, we expected them to get 24. So 32 seems a little bit high, which maybe gives us some evidence that the true value might be higher than 30% for the whole population. In fact, let's just think about what that percent is based on the sample. The sample was 32 out of 80, and sure enough, that's actually 40%. Based on their sample, they're saying that they think 40% of the population is using YouTube. So here's the question to answer now. It says, does this result provide convincing evidence that more than 30% of AP Stat students are using YouTube? Now, hopefully you're familiar with this language of convincing evidence, and I hope that it makes you think about inference and specifically a significance test. And in order to come to a conclusion in a significance test, we need a p-value or a probability. And specifically, we need the probability of getting that result or more extreme, assuming some claim is true. Well, assuming that the original claim was true of 30%, this outcome of 32 or greater is not very likely. In fact, that's what we calculated in number 5. That only happens 3% of the time, 3.6% of the time, purely by chance. So let me write that out in words here. Okay, what I'm trying to do is to interpret this probability that we calculated in number 5. So here goes. Assuming the 30% claim is true, there is a 0.036 probability of getting 32 or more YouTubers in a sample of 80 purely by chance. Now, I will tell you what, that sounds very, very familiar to me. And if you've been all the way through the course, hopefully you clearly see that this, people, is the holy grail of AP statistics. It is the interpretation of a p-value, which is the thing that allows us to make a conclusion at the end of a significance test. And here, the probability, or the p-value, is very small, less than 5%, right? Which means we do have some convincing evidence here. We don't think this happened purely by chance. So my final conclusion here is going to look similar to a conclusion that you might write for a significance test. I'm going to say, because my p-value is less than my alpha level of 0.05, we do have convincing evidence that more than 30% of AP Stat students are using YouTube. All right, so that wraps up the big idea of a binomial random variable. And remember, the second learning target we have is to investigate this idea of a geometric random variable. So let's slide over to page 2 of the activity here. And I've got a little bit of a setup here. It says, based on the College Board sample, 40% of AP Statistics students are using YouTube as part of their AP exam review. Assume now that this claim is true. Okay, so no longer are we going with the first claim that was made of 30%. We are now saying that we think that the true population proportion of AP Stat students that are using YouTube is now 40%, 0.40. And the setup here is going to be a little bit different. It says, Mr. Wilcox decides to try and find one student who is using YouTube as part of their AP exam review. He will randomly select AP Statistics students one at a time until he finds a YouTuber. So another way of saying this is, I'm going to keep taking trial after trial until I get my first success, where the success is defined as the person being a YouTuber. And here's the random variable. Y represents the number of students it takes to find a YouTuber. Now, right away, I want you to recognize that this is not a binomial random variable. And the reason is because for a binomial random variable, you have to have a fixed number of trials. And in this case, we don't know how many trials. I might find my first YouTuber on the first try, or the second try, or the 18th try, but we do not have a fixed number of trials here. So this is what's called a geometric random variable. And sure enough, to check that we have a geometric random variable, there are 4 conditions which look almost the same as the 4 conditions for a binomial random variable. So let's list them out here. 4 conditions. And 3 out of the 4 are exactly the same as they are for a binomial distribution. So that first one, the binary condition, where each trial is a success or failure, same condition. Second condition, independent, where we knew this was satisfied because we had a random sample, and also the 10% condition was satisfied, that's the same. And then number 4, the same probability of success for each trial. That's exactly the same as it is for a binomial. So the condition that's different is condition number 3, which I'm going to write as the trials condition. And what it says is that the thing we're measuring here, the variable, is the number of trials until a success. So we do not have a fixed number of trials here. We are looking for the number of trials until we get that first success. And so this right here is the condition that makes a geometric random variable different than a binomial random variable. Okay, so I'm going to go through actually the same set of questions that we did for binomial, but now for geometric. Number 8 says, what is the shape of the distribution? We're going to need to do a little bit of work to think about this one. So here's what I'm going to have us think about first. Let's first think about the probability that y is equal to 1. Now realize y can't be equal to 0, right? If we need the number of trials until we get the first success, if the first trial is a success, then our y value is equal to 1. Okay, so what's the probability of that happening? Well, we'd have to have a success on the first trial. And we know that happens 40% of the time. So that's easy enough. Now, if we think about y being equal to 2, 2 people in order to get our first success. Well, that means that the first person was a failure and the second person was a success. And they're independent, so we can just multiply probabilities. So we have a failure for the first and a success for the second. And if you put that in your calculator, you're going to get 0.24. Now let's just do one more of these, thinking about the probability that it takes 3 people to get our first success. Well, then we're going to have a failure and then a failure and then a success. So it would be 0.60 times 0.60 times 0.40. And sure enough, that's going to be 0.144. Now, what I hope you're noticing here as we move from one to the next is that our probabilities are decreasing. And the reason is because each time we move down one, we're adding one more failure at the front end, which has a probability of 0.6. So if we're multiplying by 0.6 every time, we're getting a smaller and smaller probability. This is also why it's called a geometric distribution, is because those probabilities have a common ratio, which is the probability of failure. Now, let's think about the distribution of y. If we were to graph this, y equals 1, and y equals 2, and y equals 3. Well, 1 would have the highest bar, right? If probability is represented on this axis here. And then 2 would be less than that, actually 60% of the previous bar, and then 60% of the previous bar. And you can just imagine what the rest of this distribution is going to look like. So now very clearly, I can identify the shape of the distribution as skewed to the right. Okay, next up, we are looking for the mean and the standard deviation of y. And our formula sheet here is going to give us some help again on this one. Right below binomial distribution, we have formulas for a geometric distribution. So here's your formula for the mean. And then quick note here, this formula for standard deviation is brand new to the formula sheet for 2020. This was not on the previous versions of the formula sheet, but it is now part of the formula sheet and we are responsible for it. So let's write those formulas out in the margin here. The mean of a geometric random variable is just 1 over p. And the standard deviation, according to the formula sheet, is the square root of 1 minus p, all divided by p. So now we just have to plug some numbers into this one. All right, the mean is going to be 1 over 0.4, and that's going to give me 2.5, which is telling me if we were to do this over and over again, we can expect about 2.5 trials in order to get the first success. And the standard deviation, square root of 1 minus 0.40, all divided by p. So this one is going to give us 1.94. So the number of trials until the first success is typically going to vary by about 1.94 away from the mean of 2.5. Okay, up next, find the probability that it takes exactly 5 students to find the first YouTuber. Well, once again, our formula sheet here actually has the formula, although I think we were just about to arrive at this formula in the activity. But let's go ahead and record it. The probability of getting X trials until the first success is 1 minus p, which by the way is the probability of failure, raised to the X minus 1. That's actually how many failures. And then it's going to be followed by 1 success, right? So for this particular problem, we can very easily find the probability that it takes exactly 5 students to find our first YouTuber. So that means that the first 4 students were failures. So I take the probability of failure raised to the 4th. And then the final student number 5 was a success. So we multiply by p at the end there. And this is going to give me 0.052. All right, moving on to number 11, the probability that it takes now at most 5 students, which is different than exactly 5 students. So now I'm looking for the probability that y is less than or equal to 5. Well, I could just find 5 and 4 and 3 and 2 and 1 and add them all together. But once again, just like for binomial, there is a calculator function which can help us here, which is called geomet CDF. And the arguments that you need to know for the calculator here, you have to tell it the probability of success, 0.40, and you have to tell it the number of trials there, which would be 5. And let's go ahead and see what the calculator is going to give us here. So it's found in the same menu. If you go to second vars, there's your distribution. You're going to have to scroll down a little bit further past the binomial ones until you can find geometric. And once again, you have PDF if you're trying to find exactly one value, or CDF if you're trying to find cumulative up to and including one value. And we want CDF here. And our P is 0.4. And we want 5 trials. So the calculator will tell us that we have an answer of 0.922. So let's jump back into the activity and record that, and then we have one final question to answer based on that answer. So our final answer from the calculator here was 0.922. And our final question here says, suppose that it takes Mr. Wilcox 6 students to find the first YouTuber. Does this result provide convincing evidence that less than 40% of AP Stat students are using YouTube? So we see this language of convincing evidence, which I hope makes you think inference and significance test, and maybe even p-value. So we need to know, how likely is it that this would happen or more extreme, assuming that the claim is true? Well, let's just pause right here. That value or more extreme, we are looking for the probability that it would take 6 or more students to find YouTube. Well, we know from question number 11, the probability of getting less than or equal to 5, this is just the complement of that. So I just want to do 1 minus the probability that y is less than or equal to 5, which we just calculated as 0.922. And so now I'm getting my p-value here of 0.078. So let's start with an interpretation of that, all right? So we're going to say, assuming the 40% claim is true, there is a 0.078 probability it would take 6 or more students to find a YouTuber purely by chance. Now, this p-value is greater than our alpha level of 5%, which means that we think that this result could have happened purely by chance, assuming that the 40% claim is true. So that's going to change our final conclusion here. Our conclusion now is going to say, because our p-value is greater than 5%, we do not have convincing evidence that less than 40% of AP Stat students are using YouTube. All right. So that takes care of the activity. I'd like to check back in now with those learning targets that we started the lesson with and make sure we got everything that we needed to. So in the important ideas here, I'm literally just going to cut this right in half. And we're going to have 1/2 over here addressing learning target number 1, which was about the binomial random variable. And then this one over here on the right, we're going to take care of learning target number 2, which is about the geometric random variable. So starting with binomial, I'd like to first record the 4 conditions necessary for a binomial. And remember, that's binary and independent and number which is that the number of trials is fixed, and then same probability of success for each trial. Now, quick little acronym here. Some students will use BINS to help them remember the 4 conditions needed for a binomial. Now, the one thing I want to add in here is that if you are sampling without replacement, then we need to check the 10% condition to say that the independence is okay. So 10% condition when sampling without replacement. Okay, now to describe a binomial distribution, I'm just going to handle this by going shape, center, and spread. And we decided that the shape is hopefully approximately normal. But we do have to check the large counts condition in order to be convinced that that's true. So just as a reminder, the large counts condition says that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Okay, for the center of the distribution, I'm just going to write out the formula for the mean for a binomial, which we can get from the formula sheet, and then the formula for the standard deviation, which we can get from the formula sheet, square root of n times p times 1 minus p. And then finally, the last thing I want to record here is how to calculate the probability of getting exactly x successes out of n trials, which comes from our formula sheet. N choose x times the probability of success raised to the x times the probability of failure raised to the n minus x. Okay, let's see if we can do the same thing over here on the right for the geometric distribution, starting with our 4 conditions, which are almost exactly the same. We got binary, we got independent. The third one is the one that's different because there are no longer a fixed number of trials. We care about the number of trials until the first success. And then the fourth one is the same probability of success for each trial. And sure enough, there's an acronym here that might help you remember the 4 conditions for a geometric random variable, which is BITS, B-I-T-S. And I just want to note here that we do still have to check the 10% condition if we are sampling without replacement. Okay, once again, let's describe the distribution by talking about the shape, the center, and the spread. The shape, we decided for a geometric random variable, is skewed right, and will always be skewed right. The mean and the standard deviation here, the mean is given on the formula sheet. It is 1 over p. Standard deviation is also given on the formula sheet, square root of 1 minus p, all divided by p. And the last thing I want to include here is how to calculate probabilities for a geometric distribution. So the probability it takes exactly x trials to get our first success. Well, we have a bunch of failures to start. Probability of failure raised to the number of failures, which is x minus 1, followed by a success at the end, which is p. All right, so your homework problem is here. It is a sample multiple choice question, which you can try at home, and then Mr. Murphy will go over that